we want to compute this integral dx over that. I'm going to use two methods to solve this problem to hopefully help you gain a better understanding of what's going on. So we have this definite integral. This looks pretty ugly. There's a fraction, there's a denominator. We don't like denominators, right? Can we somehow get rid of this denominator? That's the motivation. We want to beautify that. It looks ugly. How do we beautify that? Well, let's write it this way. Let's rewrite this integrand as e to the negative pi x. Does that make sense? Now it looks way more beautiful, right? There's no denominator at least. There's a negative sign, but it doesn't matter. All right, after writing it this way, let's perform a U-substitution. As a rule of thumb, we usually let U be the most complicated part. So which one is the most complicated part? This exponent, negative pi x, right? So let's let U be the entire exponent. Also, let me point out, we could let, if you recognize this entire integrand, e to the negative pi x as the most complicated part, it's also fine. You can also try and let U be this. It usually doesn't work, but in this case, it works. You can try that if you, when you feel bored during the holiday season. You try it and let U be this. If you're not bored, then you're gonna have to try that. And we have an easier way. That is a much easier way. So we let U be this negative pi x. Just go through the motions. We let U be this guy. Negative pi x. Therefore, the next step, remember what the next step is?
Differentiate.
Yeah, good, that's it. We differentiate U with respect to x. That is, I usually like to use this color. So du over dx is negative pi, right? A linear function, the coefficient is the derivative. So du is just negative pi dx. In other words, dx is du over negative pi, meaning negative 1 over pi. Let's make it smaller. Negative pi, 1 over pi times dx times du. So that's it. Just a few linear transformations. This is times dx. This is divide negative pi divided by negative pi. So now we've expressed dx as something in terms of du. So that is to say, we can replace this replace this dx in the original integral by negative 1 over pi du. So next, we write this integral as e to the u dx. Now dx is negative 1 over pi du, so negative 1 over pi du. What about the two limits of integration? Are they still 0 and 2? It'd be great if they were still 0, 2, but unfortunately that's not true. So we have to change them as well, because this 0 is short for x equals 0. Now, the dominant variable has become u. So now the number we write here should be short for u equals something, right? So when x equals 0, what is u? 0. Yeah, very good. U is negative pi x. So when x is 0, u is negative pi 0, meaning 0 by this definition. Likewise, the upper bound from 2 to u equals negative pi times 2, that is negative 2 pi, by the same definition of u. So now we just write these two numbers in the new integral in terms of u. So 0 to negative 2 pi. All right, next, let's further beautify this integral. This is a constant, right? Negative 1 over pi is a constant. So let's pull this constant out of the integral sign. We don't want the constant to bother us inside the integral. Let's let it find its own place outside of the integral. We don't like it. So let's rewrite this integral as negative 1 over pi, the constant, times the integral e to the u times du. Does that make sense? We just pulled this out. You can think of this integral sign as the cell membrane, right? It's made up of a phospholipid bilayer. Remember that in biology. Therefore, it allows the constant molecule to freely pass through its surface, right? So we can directly move this out. But unfortunately, it's impermeable to some larger polar molecules like the U molecule. So of course, we cannot pull this out, right? We can freely pull this constant in and out. Doesn't change anything. All right, next. Now it's been very easy, right? We're almost done. The answer is just the constant times the antiderivative of U evaluated from 0 to 2 pi. What is the derivative of e to the U, antiderivative of e to the U? The Phoenix function, very good, itself, right? E to the U. So e to the U evaluated from 0 to negative 2 pi, 0 to negative 2 pi. Therefore, got the answer now. Negative 1 over pi times e to the negative 2 pi minus e to the 0 minus e to the 0. In other words, negative 1 over pi times e to the negative 2 pi minus 1, because e to the 0 is 1. Anything to the 0, the power is 1. So yeah, that's it. That's problem 6. Let's call this method 1. This is enough. This is the best method. Let me also just broaden the horizon. Let's give you another method. The first step remains the same. We beautify this function by getting rid of the denominator. And next, instead of directly computing that, let's first find the antiderivative of this integrand. Because it would be great if we had a formula that tells us the antiderivative of e to the negative pi x, right? If we had this formula, then we would be able to write it this way, 0 to 2 by the evaluation theorem. And then we put the antiderivative here. We would be able to get the final answer like in one step. But unfortunately, there's no formula that tells us the antiderivative of e to the negative pi x. We know the antiderivative of e to the x, but we don't know the antiderivative of e to the negative pi x. So what should we do?
Ln?
Oh, you mean ln both sides and
Yeah.
Yeah, that's a good approach. Let's see if that works or not.
I don't know how that would work if you're trying to.
No, I don't think that would work because that's inside the integral.
Yeah.
Like ln cannot pass through the surface, right? So numbers. So instead, let's do it this way. So let's follow what I said. First, we try to find the antiderivative, antiderivative of this integrand of this e to the negative pi x, e to the negative pi x. Another way of writing the antiderivative of e to the negative pi x is this integral symbol, e to the negative pi x dx. Well, let's compute that. Do you know how to compute this? That is the corresponding indefinite integral without the two bounds. There's no bounds anymore. Well, by the first method, let's perform the same U-substitution used in the first method. We're going to get by doing the same thing, except for this part. We don't have to change the limits anymore because there's no limits now. So we get by doing the same thing. Let's copy that directly. Let's let U be the same thing. And we erase this second line here because there are no limits. So we get the answer is the integral e to the u times negative 1 over pi as above. So we can directly copy this guy here. We can directly copy this and then erase the two bounds. It equals that because u is negative pi x. So we replace negative pi x with u, and dx is negative 1 over pi times du, right? Negative 1 over pi times du. So just do exactly the same thing as above. So we get this antiderivative. And then finally, of course, we use the formula, antiderivative formula to compute this antiderivative of e to the u du. That is the antiderivative of e to the u, which is itself, right? So -1/pi times e to the u by the anti-derivative formula plus a constant c. Therefore, that is -1/pi. As a good habit, we usually change everything to be in terms of x back to x. So e to the -pi(x) plus c. Now we've got the formula, right? We've computed this formula, the formula of the antiderivative of e to the -pi(x). Now we can replace this. We can directly plug that back to the first line, right? So we're done. We're almost done now. We just plug that in, and then compute this. We get the same answer. That's method 2. Doesn't matter if you didn't follow this method 2 because method 1 is the most commonly used method. That's enough for the example. Method 2 is only for driving, right? And the one benefit of method 2 is that we don't have to change the limits, right? I never changed the limits from in terms of x to in terms of u. So that's the beauty of it. The beauty of method 2. We directly plug in x equals 2 and x equals 0, and we get the final answer because we've already changed everything back to x, in this step. So that's it.